the Lord has made. Good morning, all. Today we are going to be reviewing some of the things we did last week. I'm going to be sharing my screen with you. And sorry. Just a moment. Oops. I'm trying to open the file. So I'm going to share with you. Share screen versus some printers now. Oh. Okay. Please be patient. I think they keep modifying things on Zoom. So I don't know. I'm trying to pick the file to share. Okay. I think I should be able to get it now. Yeah. I hope you can all see my screen. I think so. Okay. Today we are going to continue. We are going to review some of the things we learned last week. And it's the concept of electromagnetic induction and applications. When last week we learned that no current is produced in a loop of wire that is stationary in a constant magnetic field. And today we are going to review that with an illustration, with some illustrations with this diagram. So I'm going to pick a pointer with which I can show you what is going on. Okay. So if you look at the diagram label, it says no motion between magnet and loop. It has been observed experimentally that a magnet held stationary, this is a magnet, this is a loop. So it has been observed experimentally that a magnet that is held stationary near a conducting wire loop, this is a conducting wire loop, does not induce an EMF and so produces no current in that loop. And what is EMF? Enoch Ogunleye, please turn off your video. Turn off your video. Unless you want to take over the class from us. And by the way, excuse me, I just want to take some water. So as I was saying, experimentally, when a magnet is held stationary near a conducting wire loop, it does not induce any EMF in that loop. And so it does not produce any current. So what do you understand by the term EMF? EMF stands for electromotive force. And it is a voltage or electric potential difference, which is capable of creating an electric current. So when we say EMF is induced, EMF is not induced, all what you're talking about is the ability or capability of creating an electric current. So in this case, no electric current is created because the magnet is stationary and the wire loop is stationary. And you can see that the galvanometer is not giving us any readings. So no motion between magnet and loop. But if we look at the other diagram, you see that the magnet is moved towards the loop. You can see that the distance is now closer. The distance of the magnet between the loop is nearer than it is in A. So if the magnet field changes with time, and if the wire loop moves into or out of, or is rotated in the field, a current is produced in the wire. That was what we studied last week. I'll repeat that. Last week, I told you that if the magnetic field changes with time, or if the wire loop moves into or out of, or is rotated in the field, a current is produced in the wire. So looking at the diagram labeled B, we can see that moving the magnet towards the loop increases the field of the number of field lines passing through the loop. Here we have, if we count, we have about 7. Here we have about 12 field lines passing through the loop, and an induced current is detected. So we can detect an induced current here, but only during the motion, So you can see that the galvanometer needle has deflected towards the left. So let's see what happens when the magnet is moved away. It's moved away from the loop. Says, see, magnet is moved away from the loop. Ojo Abiola, you are distracting us. Ojo Abiola, turn off your video. Thank you. So moving the magnet away from the loop decreases the number of lines passing through the loop. When the magnet is moved away from the loop, it decreases the number of lines passing through the loop. If you count here, you can see about 5 lines passing through the loop. So the induced current is now in the opposite direction. You can see that the induced current is now in the opposite direction to this one. This one is to the right, is to the left. And the galvanometer needle has deflected to the right. So in general, when the magnet was moved, the magnetic environment in the loop changed. Caused an induced EMF, that's electromotive force, in turn caused an induced current. Adams Michael, turn off your video, please. Adams Michael, turn off your video. So we go to the next slide. Sorry, maybe I have to. It seems not to be responding. I don't know. I'm trying to go to the next slide. Okay. I think that's it. So experimentally, there is an exception. I'll pick the pointer again. Okay. So experimentally, there is an exception. If a loop is moved are not rotated parallel to a uniform field, no current is induced. As we can see now, the magnetic field is parallel and the loop is moved parallel to the uniform magnetic field. So no current is induced. The galvanometer pointer is on 0. So no change in the number of field lines passing through the loop. So the next slide is on mutual induction. Let's hope I'll be able to change fast. Okay. I'm sorry. Seems to be a bit slow in changing. Page down, page down, page down. I wonder why it's doing this. Okay, so the next slide is on mutual induction. And it is another way to induce current in a stationary wire loop. So the mutual induction is the term used to describe the situation in which EMFs and currents are induced between two or more loops. Okay, so if we look at the first diagram, let me pick my pointer again. If you look at this diagram, diagram A, you can see a wire loop connected to a galvanometer. There's another wire loop connected to a battery, and this is the key of the. So when the switch is closed, when the switch of this setup is closed, the buildup of current produces a changing magnetic field. The buildup of current produces a changing magnetic field. In the other, a changing magnetic field in the other loop, inducing a current in it. So current is induced by the changing magnetic field on this second loop. So when the switch is opened, like in the case of B here, when the switch is open, the magnetic field collapses. You can see the magnetic field is collapsing here, collapses, and the magnetic field in the left loop decreases. It decreases here. So induced current in a loop occurs only when the magnetic field through that loop changes. So another way to induce a current in a stationary wire loop is to vary the current in another nearby loop, vary the current. And we go on to the next slide. That's on now. Let me see. Good. So the important factor about electromagnetic induction is what Faraday scientist discovered. And he discovered that an induced EMF is produced in a loop of complete circuits whenever the number of magnetic fields passing through the plane of the loop or circuit changes. That is like summarizing what electromagnetic induction is. Okay. So the next slide is talking about magnetic flux. Let's see how fast we can get that. Beautiful. So magnetic flux, we discussed this last lecture. I'm just trying to review some of the things we did last lecture. It was like I did like a summary of some of the topics, but today I just want to go into a little bit of details of those topics. So, but we'll see how fast we can go. What's the time? Yeah, we still have some time. So since the induced EMF in a loop depends on the rate of change of the number of magnetic field lines passing through it, determining induced EMF demands that the number of field lines through the loop be quantified. So we shall consider a loop of wire in a magnetic field. The number of magnetic field lines through the loop depends on, let me pick my pointer quickly. Okay, we are here. So the number of magnetic field lines through loop depends on the loop's area, its orientation relative to the field, and the strength of the field, the loop area, the orientation, and the strength of the field. We don't have any problem with the loop area because we all know what area means, you know. So the orientation is, we are going to deal a little bit on that, and the strength of the field. So to describe the loop's orientation, you know, the concept of an area vector is used or employed. Its direction is usually normal to the loop's plane, and its magnitude is equal to the loop's area. You'll see that in the next slide. But here, what is magnetic flux? It's a measure of the number of field lines passing through a particular area A, and is given as phi equals to B, that's the magnetic field strength, times the area, the magnitude of the area, cos theta, where the magnetic field strength, magnetic field is assumed constant. And what is theta? Theta is the angle between the direction of the magnetic field, take note of that, the direction of the magnetic field and the area vector. And the SI unit of magnetic flux is Tesla meter squared or Weber. You either say Weber or Tesla meter squared. If we go to the next slide, talking about magnetic flux, several possible orientations of the magnetic flux. Before that, let me go back to this one. And you might be wondering why the cosine term. The orientation of the loop with respect to the magnetic field affects the number of field lines passing through it. And this factor is accounted for by the cosine term. It's accounted for by the cosine term. So let's look at the several possible orientations, because we said that the orientation, the number of magnetic field lines through loop depends on loop's area, the orientation relative to the field, and the strength. So now, let's look at the several orientations. So this is the loop of wire in a magnetic field that we are talking about. If the direction of the magnetic field and the area vector are parallel, theta is equal to 0, like we have here. Theta is equal to 0, then the magnetic flux is positive and have a maximum value of magnetic flux. That is, has a maximum value of phi. And it is given by this equation, phi maximum is equal to the magnetic field times the area cos theta, cos 0, sorry. Oh, I thought I was using the, sorry, let me pick my pointer. Okay, here we are. BA cos 0 is equal to plus BA. Why? Because cos 0 is equal to 1. I'm sure we all know that by now, even from secondary school. So 1 times this gives us this. So the maximum possible number of magnetic field lines pass through the loop in this orientation, when the direction of the magnetic field is parallel to that of the area vector. So the second possible orientation is this. If the direction of the magnetic field and the area vector are oppositely directed, you can see it's now in the opposite direction. Theta is equal to 180 degrees. Then the magnitude of the magnetic flux is a maximum again. but of opposite sign, Why is it of opposite sign? Because 180 degrees is -1. So we have minus BA. We have the flux, maximum flux, but of the opposite direction. Now we look at the other orientation, type of orientation that can happen or occur. That is the direction of the magnetic field and the area vector are perpendicular to each other. Mind you, this is the direction of the magnetic field. Then there are no field lines passing through the plane of the loop, and the flux is 0 because 90 degree is what? Is 0. Because 90 degrees is 0. So 0 times anything is 0. That's even from primary school. You must have learned that from your primary school. Okay. So the last type of orientation that can occur is this. For situations at intermediate angles, at any angle, intermediate angles, the flux is less than the maximum value, but it's non-zero. So A cos theta can be interpreted as the effective area of the loop perpendicular to the field lines. So in general, flux is equal to BA cos theta. So we are moving on to Faraday's law of induction. We discussed this last week, but the equation here is a bit different from the one you had last week, but it's still the same definition, only I added this other one. So the Faraday's law of induction relates the induced EMF in a loop or coil composed of, let me pick the pointer one moment. Faraday's law of induction relates the induced EMF in a loop or coil composed of n loops in series to the time rate of change of the magnetic flux through that loop or coil. So this is the formula for Faraday's law for induced EMF. Epsilon is equal to minus n delta phi over delta t, and it can also be written this way, where delta phi is the change in flux through one loop and there are n total loops. The negative sign gives an indication of the direction of the induced EMF. We saw that last week. So the next slide is talking about Lenz's law. A Russian physicist named Heinrich Lenz discovered the law that governs the direction of the induced EMF. And it might interest you to know that he existed between 1804 and 1865. So there's really nothing new in physics, okay? There is really nothing new. Only, well, a little bit of inventions here and there, but the basic physics is the same, has been the same over the years. Imagine we are studying something that somebody that died 1865, what he discovered is still relevant to physics today. So there's really nothing new under the sun, okay? So don't go and hang yourself when you are passing through some issues in life and say, oh, it's all about me, I'm alone. I know I'm deviating from physics a little bit, but physics relates to every aspect of life. That's why physics is very interesting. And that's why I love physics anyway. If you don't like physics, it's your problem. Excuse me 1 minute. So we continue. I know some people are smiling, but we are not permitted to show your face. So Lenz, as I said, was a Russian physicist, and his law states that an induced EMF, let me pick my pointer. Okay, sorry. An induced EMF in a wire loop or coil has a direction such that the current it creates produces its own magnetic field that opposes the change in magnetic flux through that loop or coil. So what's the meaning of this? It means that the magnetic field due to the induced current is in a direction that tries to keep the flux through the loop from changing. That's the law of Henry's length. We mentioned that last week, but we didn't include the meaning. So that's why today's class is a review of what was taught last week. And if we have enough time, we'll do something new. Okay? But I don't want to rush you too much. And because your understanding of what is being taught is very important. So for example, if the flux increases in the positive direction, let me pick my pointer, second, okay. If the flux increases in the positive X direction, as you can see in the diagram below, the induced current will create its own magnetic field to try to counteract the flux change that is occurring. And how does that happen? You can see that from this, the direction of induced current given by the induced current right-hand rule. There's something called induced current right-hand rule. It states that with the thumb of the right hand, if you take your right hand and it's with the thumb of the right hand pointing in the direction of the induced field, the fingers coil, something like this. The fingers coil in the direction of the induced current. That is the induced current right-hand rule. So it gives the direction of the induced current. The coiled fingers, the fingers that is coiled, gives the direction. And you can see it here. You can see somebody's finger here. You can see the thumb. The thumb is pointing in the direction of the induced field. And you can see that the induced field is in the opposite direction. So the magnetic field due to the induced current will be in the negative direction. That's what you are trying to say. That if the flux increases in the X direction, this is a flux increasing in the positive X direction, the induced current, this is the induced current, will create its own magnetic field to try to counteract the flux change that is occurring. So this is negative, positive. This is trying to counteract the positive, the increase in flux that is occurring. Oyegunju Gbemisola, turn off your video, please. Oyegunju Gbemisola, turn off your video. Thank you. So that is it. So this is the right hand. This coiled fingers is showing us the direction of the induced current, whereas the thumb is pointing in the direction of the induced field. And we learned last week that the induced EMF has the same direction as induced current. So we go on to the next slide. Oh, okay. Let me continue sharing from the last file. Okay, so I'll stop sharing this. I'll go and pick the last, the file we had last lecture. Okay. Just a moment. I want to share this file now. Okay, so on slideshow. So this was what we discussed the whole of this. I've reviewed all that. Then we talked about applications of electromagnetic induction. We talked about motors, electric generators, transformers, credit or debit card readers. So we talked about electric motors. I'm just reviewing this again, that a motor has a rotating armature in a magnetic field, And the motor device is a device that converts electrical energy into mechanical energy. We looked at all this last week. And motors usually generate induced EMFs at the same time. And we looked at some important applications, some components. We said that electric motors are important components in electric fans and all that. And we looked at the working principle. And we said that a motor has a rotating armature in a magnetic field. Let me pick my pointer again. Rotating armature in a magnetic field. For motors, the induced EMF is called a back EMF. We discussed that. We talked about back EMF, and we said that a back EMF or counter EMF is induced in the coil. This back EMF opposes the voltage source that drives the motor. And the back EMF is so called or so named because its direction is usually opposite that of the line voltage. The direction of a back EMF is usually opposite that of the line voltage and tends to reduce the current in the armature coils. That's why it's called back EMF. I'll put my pointer again. So back EMF, remember wondering why back EMF or counter EMF, is because its direction is opposite that of the line voltage, and it usually tends to reduce the current in the armature coils. So the polarity is usually opposite that of the driving voltage. So we have the net potential difference being equal to line voltage minus back EMF, and we have the current equal to this formula. Go to the next slide, just reviewing this. And just a moment, if we go back. So the current is equal to the net, assuming we call this the net voltage, either net PD or net voltage. So what we have here is net voltage over the armature resistance. The net voltage over the armature resistance. And if we look at the definition of the net voltage is line voltage minus back EMF. So the back EMF is equal to the voltage minus current times resistance. I don't know whether, if you make the back EMF the subject of the formula here, what you will have is V minus, that's the line voltage minus the products of current and resistance. That's mathematics. So mechanical power, that is the power developed within the armature of a motor, is given as the current times the back EMF. We saw that last week. I gave you a worked example, which I believe all of you attempted to do. So take notes. I just want to, before we go on to generators, I just wanted to take note that the back EMF of a motor depends on the rotational speed of the armature and increases from 0 to some maximum value as the armature goes from rest to its normal operating speed. So let me see if we have enough time. Yeah, I still have some time. We still have some time to quickly review this. Electric generators is a device that converts mechanical energy into electrical energy. We saw this last week. And we said that an external source, such as a steam turbine, turns the armature coil in a magnetic field B. The wires of the coil cut the field lines and an EMF is created. I mean, this was just, we bypassed a lot of things to get here. So make sure you study very well. You can use any physics textbook. Holiday is okay. College Fundamental of Physics is okay. College Physics is okay. And there is a textbook, Fundamentals of Electricity and Magnetism. It's also okay for this course. I don't know if you were told that before. So when the loop is rotated at a constant angular speed, let me see the diagram of a generator. Okay. Let me just discuss the equation from here. When the this loop is rotated at a constant angular speed, omega, the angle theta between the magnetic field vector and the area vector of the loop changes with time. So theta will be equal to omega t, assuming that theta is 0 degrees at time t equals to 0. So as a result of the field lines through the loop, as a result, let me pick the pointer. I thought I was using the pointer. Yeah. As a result, the number of field lines through the loop changes with time, causing an induced EMF. So the flux for one loop varies as phi equals to BA cos theta, as we said earlier. Let me go back to the equation. I'm just trying to let you know how we arrived at this equation. If you can write it down, it will be good. I expect that you always come to class with your notebook and your pen, okay? Even though the class is being recorded, I still expect a good student to have his or her exercise book or notebook by his or her side and the pen. So if you care to follow what I'm trying to say, you can put it down. I said, starting with the flux. Flux is equal to phi equals to BA cos theta, which is equal to BA cos omega t. So for a rotating coil of n loops, Faraday's law yields epsilon equals to minus n delta phi over delta t, like we saw earlier. And this is equal, if you expatiate, if you impute phi into that Faraday's equation, if you expand the Faraday's equation by substituting for phi, you have epsilon equals to minus capital letter N, capital letter B, capital letter A into delta cos omega t over delta t. I'm just trying to show you how we arrived at this equation. So B and A are constants. So they are out of hence they have been removed from the time rate of change. So they are not within the time rate of change. So what you have is delta cos omega t over delta t and times minus NBA. So minus NBA in front as constants and delta cos omega t over delta t. And if you evaluate this equation further, the induced EMF can be written as NBA omega sine omega t. So that's another way by which this equation can be written. And I think you should write it that way. Epsilon equals to NBA, this is NAB, well, it doesn't matter whether it's NAB or NBA. NBA omega is 2 pi F. Omega is 2 pi F. So 2 pi F, omega is equal to 2 pi F. So it's still the same thing. But instead of course here we have sine omega t. That's sine 2 pi F t. So the NBA omega, this term here, represents the magnitude of the maximum EMF. The magnitude of the maximum EMF, which occurs whenever sine omega t is equal to plus or minus 1. I told you that the omega t, the new equation now is NAB or NBA omega, which is the same as NBA 2 pi F, which is here. We now have sine omega t, represents the magnitude of the maximum EMF, which occurs whenever sine omega t is equal to plus or minus 1. And when is sine omega t equals to plus or minus 1? If we say theta is equal to omega t, that's when theta is equal to 90 degrees or 270 degrees. So if we say that this is equal to epsilon naught, so we have an equation which is equal to epsilon equals to epsilon naught sine omega t. Sine omega t. So take note that at the point, at the instant when the plane, at the instant when the plane of the loop is parallel to the field and phi is equal to 0, the EMF will be at its largest magnitude. The EMF will be at its largest magnitude. So for a current to be induced in a coil, we looked at this last week. We go on to, that was an example. I told you that during the last week of lectures or thereabouts, we are going to have a revision class, and there we can like solve all the questions, all the worked examples, and look at more questions. It will be like just a tutorial class or something like that, a revision class. So today we are going to look at something new, and it's about transformers. A transformer is a device that changes the voltage supplied to it by means of induction. And it consists of a primary input. Let me pick my pointer again. Okay. It consists of a primary, that's the input, and a secondary, that's the output coil, wound on the same inner coil. Sorry. Let me minimize this. The same iron core. You'll be hearing my voice now, or you are not seeing my face, but you know I'm here. Don't worry. We are all here together. So an alternating, because the video is blocking some of the words. So that's why I minimized it. But you see Dr. Obed talking. An alternating current in one coil creates a continuously changing magnetic flux through the core. And this change of flux induces an alternating EMF in the other coil. Take note that it is common in transformer design to refer to EMFs as voltages. The next slide. Still under transformers, if we look at Faraday's law again, Faraday seemed to have laws for different aspects of electromagnetic induction. So by Faraday's law, the induced voltage in the secondary coil is Vs equal to, let me pick my pointer so you can follow what I'm saying, is Vs equals to Ns delta phi over delta T, where Ns is the number of turns in the secondary coil. The changing flux in the primary coil produces a back EMF or a counter EMF of Vp equals to minus P delta phi over delta T. Delta phi is the flux, change in flux, where Np is the number of turns in the primary coil. And you'll be wondering which one is the primary coil, which one is the secondary coil. Let's see that in a diagram shortly. Oops. Okay, don't worry. Okay, we are not here yet, but I'll just show you briefly. This is the secondary coil winding. This is the primary. Okay, so we go back to, we are not here yet. A ratio of output voltage to input voltage is given as Vs over Vp equals to Ns over Np. This is the voltage ratio in a transformer. This is the voltage ratio in a transformer. If the transformer is 100% efficient, you know, that is, there are no energy losses. When you say transformer is 100% efficient, it means that there are no energy losses at all. So the efficiency of a transformer is usually very high anyway, even if it's not 100%. Then, if it's so, sorry, if the transformer is 100% efficient, that is, there are no energy losses, then the power input, excuse me, sorry, the power input is equal to the power output. So we see that power in primary is equal to power in secondary. And going to the next slide, you begin to wonder, what is a step-up transformer and what is a step-down transformer? A step-up transformer has more turns in the secondary coil than in the primary coil, okay? So it has more turns. You can see a lot of windings. Oh, my pointer. You can see a lot of windings in the secondary coil than in the primary coil. This one's are scanty, this one has a lot. So it has more turns than the primary winding. That is, Ns, the number of turns, over the number in secondary, over the number of turns in primary, is greater than 1. The voltage is stepped up because Vs is greater than Vp. That is, the changing flux in the primary, the back EMF in the secondary is greater than the back EMF in the primary. Because of this, there is less current in the secondary than in the primary. So Np over Ns is less than 1, and Is, that's the current in the secondary, is less than the current in the primary. So that's an illustration of a step-up transformer. We go on to the next slide. Then we talk about step-down transformer. Step-down transformer has more turns in the primary coil. I pick my pointer again, and this is the primary coil. So a step-down transformer has more turns in the primary coil than in the secondary coil. So the voltage is stepped down and current is increased. That's the relation. So if the secondary coil has fewer turns than the primary does, we have a step-down transformer, like I said. In the usual transformer language, this means that the voltage is stepped down. The voltage is stepped down and the current, therefore, is increased. So depending on the design details, a step-up transformer may be used as a step-down transformer by simply reversing output and input connections. I will repeat that again, that depending on the design details, a step-up transformer may be used as a step-down transformer by simply reversing output and input connections. So let's look at the next slide. The next slide is a worked example. It says a step-up transformer is used on a 120 line to furnish 1,800 volts. The primary has 400 tons. How many tons are on the secondary? The answer is 1,500, but this is the formula you use. Use this formula, work it out, and you should use this formula, work it out, you should get this answer, okay, with the correct, how many tons? Okay, no unit. So I think this is a convenient place to stop today. Thank you all for listening. Have a great, good week. Bye for now.
Hello, everyone. A quick announcement, please. Our CA will be coming up on Wednesday, and the time is 8 a.m. The venues will be on our notice boards today at department, and I will also put a copy of it on the LMS page so that you know your venues. And at the end of the tests, your class for 9 a.m. will still hold, which is, I think, is a zoo course. It will start at 9:30 a.m. So thank you.
Thank you very much, Dr. Shakwande, for that announcement. I actually forgot. So have a nice day.